If you've made it through group theory, we continue with ring theory. Here, our ultimate goal is to lay down foundations for number theory and Galois theory. But we'll see other interesting results along the way. Now, as with group theory, rings are going to come in many shapes and sizes, so we're going to want a nice stable of examples to match our intuition to the theory. For this part, we'll just give definitions and these examples. Now, when I think about rings for the first time, everything is going to be pretty much based off of what we can do with the integers. So, for instance, when we talked about groups, we talked about a set with a single operation. But we know many groups which have two operations, integers being our primary case. So, a ring is going to be a set with two operations, an addition and a multiplication. It'll have the following properties. Under addition, a ring is going to be an abelian group. We'll call the identity 0. Under multiplication, we don't insist on the full group properties. I'll just want that our ring is closed under multiplication. Then, to make sense of the addition and multiplication at the same time, we have the distributive law. So this should be familiar. Now for us, we're going to insist on two of the other group operations for multiplication. We'll want that our rings are associative under multiplication. So that just means when we multiply, I can remove the parentheses. And we'll want a multiplicative identity, usually. So this is going to be an element 1 not equal to 0, such that 1 times x equals x times 1 is equal to x for all x in the ring. Now, sometimes we don't have a 1 in our ring, and then we just call it an RNG. So we take the I out of ring. We need not insist on our multiplication being commutative. So the addition is always commutative, not necessarily the multiplication. If multiplication is commutative, then we'll just call R a commutative ring. So here when we talk about commutative, we're talking about the multiplication. Basic examples. So like I said before, the first ring we encounter is the integers. So the integers, all of our definitions up to here are based on the integers. Then, integers sit inside the rational numbers, sit inside the real numbers, sit inside the complex numbers. So far, these are all commutative rings. From the integers, we can also pass to modular integers. So there we have addition as usual, clockwork addition. And then we have multiplication, which also works. So we have a clockwork multiplication, just by adding or subtracting multiples of n. Now, for these commutative rings, what we can do, the operation of adjoining, I could pass from our ring to our ring adjoin x. So what it means to adjoin x, this is just going to be forming the set of polynomials, in the variable x, with coefficients in our ring. We say that as over the ring. So you'll note, if we have polynomials, there's going to be some highest degree. If I multiply two polynomials together, I get another polynomial. So this set's going to be closed under our usual multiplication of polynomials. If we add two polynomials together, we get another polynomial. They can just start working through our list. We can adjoin objects other than a variable x. For instance, if I take the integers, I can adjoin square root of 2. That's not in the integers. This is going to be the polynomials in square root of 2 with coefficients in the integers. To describe all of these elements, well, if I have a polynomial in square root of 2, with a constant term, I have a square root of 2 term. If we take square root of 2 and square it, we get back 2, which is an integer. So we're going to wind up back here. So I only need 2 integers to describe every element in here. For the cube root of 2, we'll only need 3 integers to describe all of these elements, and so on. Now, an example we'll come back to later. We have the Gaussian integers, so we're going to take the integers and we're going to adjoin I. So this is a subset of the complex numbers. We have I squared equal to -1. Now, these three examples, something special about these, which we'll note. Consider the example z adjoin pi. So this is going to be the polynomials in pi with coefficients in the integers. We won't have a description of these that's as simple as these three examples. Okay, the idea is pi is a transcendental number. So that means pi is never going to be a root of a polynomial with coefficients in the integers. So we're not going to be able to have a description like one of these three. In fact, if we adjoin pi, okay, this is almost the same as just adjoining x. And we'll make that precise later on. Now, okay, to contrast with transcendental, I would call square root of 2, cube root of 2, algebraic numbers. So that means these numbers are going to be roots of some polynomial over the integers. Okay, so square root of 2 is a root of x squared minus 2. Cube root of 2 is a root of x cubed minus 2. Now, we've only considered so far commutative rings. How about some non-commutative rings? So here we want the multiplication to be non-commutative. First example from linear algebra. Okay, so we'll use a commutative ring R just to keep things simple. I could take the n by n matrices with entries in R. So if you've taken linear algebra, you've seen m sub n of the real numbers, and you may have seen m sub n of the complex numbers. If we have n equal to 2, okay, so we're just looking at 2 by 2 matrices, our addition is going to be coordinate-wise, okay, as so. For the multiplication, somewhat more complicated. It's going to be row-column multiplication, and that's something that you can look up. Now, things to note, for the additive identity, we just have the matrix full of zeros. For the multiplicative identity, okay, we're going to have ones on the diagonal, zeros off. And we could also check pretty easily that this multiplication is not commutative. So we have a non-commutative ring here. For another example, let's consider the Quaternion ring. Now, recall how the Quaternion group works. We have 8 elements, plus minus 1, plus minus I, plus minus j, plus minus k. For the multiplication, we have the following rules for the letters. So if I have I squared, j squared, k squared, they're all equal to minus 1. If I multiply I times j, that's equal to k, is equal to minus j times I, and so on. So the way we summarize this, we put our letters in a circle going counterclockwise. If we multiply any two going counterclockwise, we get the third. If we multiply going clockwise, we get the third, but with a minus sign. Now, for the Quaternion ring, okay, we call these the Hamiltonians, so that's why we have an H. It's going to be a vector space over the reals of dimension 4. Okay, we have a basis, 1, I, j, and k. Okay, the addition is pretty natural. For the multiplication, we use the rules given from the group. Now, additive identity is 0, multiplicative identity is 1, and by definition, Quaternions are not going to be commutative. So I times j is not equal to j times I. It's equal to minus j times I. We could check all the properties for a ring. Okay, the only thing we lose in our list is going to be the commutativity. Now, an interesting thing about Quaternions is that they fit into a bigger picture. So there's a bit of machinery that lets us go from the reals to the complex numbers, from the complex numbers to the Quaternions, then from the Quaternions to what we call the octonions or Cayley numbers. Okay, these are going to be a vector space over the reals of dimension 8. With this process, as we move from left to right, we start losing things. So as I go from the reals to the complex numbers, we lose the total ordering, the less than or equals. As we go from the complexes to the Quaternions, we lose commutativity. As we go from the Quaternions to the Cayley numbers, we lose associativity, and so on. Now, there's still one last group property we haven't addressed, okay? The notion of inverse. So let's take a look at that now. Recall, okay, if I have an element x inverse, call that the inverse of x if we have x times x inverse equal to x inverse x equal to 1. In this case, okay, in our rings, we'll call x a multiplicative unit. Now, when we can find inverses under multiplication for all elements except 0, we have a special ring that we call a field. So I'll say that f is called a field if f is a commutative ring. Every non-zero element x has a multiplicative inverse. Now, the prototype for a field is not going to be the integers. Instead, we use the rational numbers. Also note, the real numbers satisfy these properties, complex numbers satisfy these properties, and we'll have a few others. Later we'll see, alpha is algebraic. Then if I take the rationals and adjoin alpha, that's a field. For instance, if we take Q adjoin square root of 2, okay, we take a generic element, so a plus b square root of 2, I take the inverse. So I can write that as 1 over a plus b square root of 2. How do I get the square root of 2 out of the denominator? Well, we just use rationalization. So I multiply top and bottom by a minus b square root of 2. Now, in the denominator, we'll have an a squared minus 2b squared. We have to worry about that being equal to 0, but that'll never be equal to 0 because we have square root of 2, not a rational number. So you'll note this inverse is in Q adjoin square root of 2, since a squared minus 2b squared is a rational number. How about something like Q adjoin the cube root of 2? Well, this trick isn't going to be so useful here. So instead what I would do is we just use the formal definition of inverse. So we're looking for a y such that x times y is equal to 1. So if I took a plus b cube root of 2 plus c cube root of 2 squared, if I want the inverse of that, I don't put it under a 1. Instead, I just take another element in q adjoin cube root of 2 and try to solve for a prime, b prime, and c prime when we multiply and get a 1. So that I'll leave to you as an exercise. To contrast, let's take Q adjoin pi. This is not a field. So the idea here, let's consider the element x equal to pi itself. If we assume that x inverse is in here, well, that would mean I could write x inverse as some polynomial of pi. If this element existed, then, well, we multiply that by pi, we get a 1. So rearranging terms, that means that pi is going to be a root of, okay, some polynomial, x times f of x minus 1. Now, this is a polynomial over the rationals, but I could just as easily make it a polynomial over the integers by clearing out all the denominators. So if I could do this, this would show that pi is algebraic, and that's a contradiction. Now, another example, slightly different. If we pick p a prime integer, then we can consider the modular integer z mod p. Now, to make this work, we invoke Bezout's identity. So this is for the integers. So if I have two integers m and n, whose greatest common denominator is equal to 1, I can always find integers j and k such that j times m plus k times n is equal to 1. Now, if I let n be equal to p in my statement, if we pick an x that's non-zero, so that'll represent the m, greatest common denominator of x and p is equal to 1. So when we pass to z mod p, I'll have that j times x is equal to 1. That means I found the inverse for x, and that's going to be the j. Note here, this doesn't give us much help in actually finding j. So for now, we just go to special cases. For instance, if I'm in z mod 5, okay, we have 2 times 3 is equal to 6, which is equal to 1. So 2 is inverse to 3, 3 is inverse to 2. If we take 4 times 4, we get 16. That goes to 1 also, so 4 is self-inverse. One more field-related item. Let's consider the Quaternion ring. Here, every non-zero element has a multiplicative inverse. Now, because the Quaternions are not commutative, okay, we call it instead a division ring. If we have alpha non-zero given as follows, the formula for the inverse is given here. I'll leave it to you to check that alpha times alpha inverse is equal to 1. Final construction, let's consider the direct product of rings. So we assume we have two rings, R and S. For the set, we'll take all ordered pairs. Okay, we have R in the first slot, S in the second. We have a natural addition and multiplication. Okay, we do both coordinate-wise. For the multiplicative identity, we have 1, 1. For the additive identity, we have 0, 0. Now, if we use this construction here, the direct product of two fields will not be a field. So to see this, let's just consider the element 1, 0. Okay, that's not equal to 0. We'll show that it doesn't have an inverse. Now, if I go fishing for an inverse, say r comma s, okay, I multiply 1, 0 by that, we set it equal to 1, 1, the multiplicative identity. When we solve, we see from the second coordinate we get 0 equal to 1. By assumption, that's not true. So I can never solve this equation to get our inverse. So not a field. Now, one use we have for direct product, okay, if I have G a finite abelian group, the fundamental theorem of finite abelian group says we can write G as a direct product of cyclic groups. Now, with the direct product, I can now put a multiplication on our finite abelian group. So every finite abelian group can be made into a commutative ring.